Let me go over the agenda first. And so here's our agenda. Oops. In facilitator school, I learned you always have to use two colors on your diagrams. So there we go. So the agenda today is first I want to talk a little bit about assignment 2. If you haven't turned it in, it's just about time to turn it in. And I've got assignment number 3 for you that I'm going to get out to you, and we'll go over that. So that's the first thing I want to do is kind of go over what's in assignment number 3 and field any questions that you have on those. Second thing is we'll be back finishing up regression, and I want to do a slight recap on simple linear regression, and then also we'll pick it up in multiple regression where we were sort of half done, but I want to make sure that we get those two. And then there's a couple of things that are sort of gravy, but I think you'll see why they're helpful. One is polynomial regression, which is going to be good for, remember, simple linear regression was good for fitting a line to data when I had one driver and one output, one independent variable, one dependent variable. Multiple regression is good if I have multiple variables that I'm going to use for prediction. Polynomial regression is good if I have curves. So what happens if there's a curved relationship? Indicator, and then we'll cover indicator variables, which are good for what happens if I have one of my predictors that I want to use is a category variable. In classical regression, I'm sunk, but in sort of modern regression, you're not. You can throw that into the mix and use that as a predictor, and we'll show you how to do that. And then I want to talk a little bit about DOE. Technically, I think this is supposed to be our first lecture on week 6. Week 6 is primarily design of experiments. Now, there's a lot of slides in the design of experiments section. I will be very happy if all of you basically just get the whole idea of design of experiments, like what are the advantages of it, and then sort of how do I functionally get the basics done? Because I'll tell you, just knowing the basics of design experiments, it's a super powerful tool. So we're going to walk through that today and hopefully just do an example, and then we'll probably go through examples that are in slides and so forth on the next day that we're back. Oh yes, and the announcement, and this is for real this time, we don't have class next week, so I'm going to send out 2 cancellations. It's not for the rest of the class, it's just for the Tuesday and the Friday of next week. And that was a planned one, so I think we're all on track. So let's see, I want to make sure I've got the recording going. Okay. We're all set going with the recording. So I guess I'll start with asking, what questions do you have about what we talked about last time, which was we talked a little bit more about hypothesis testing, and we talked about regression. We talked about simple linear regression, or just questions in general about assignments, so forth. Okay. Awesome. Okay. So let's before we do anything else, let's talk about the assignment that I'm going to send you today. Now it's a mix of it's essentially a mix of regression, linear regression, and design experiments. So that's basically what it is. So let's kind of walk through what's in there, just that we're all on the same page. I'm giving you till the 24th to do it. Now it seems like a long time. We have this week off, but remember, we're only covering the basics of design experiments. So if you want to read ahead, or you can also watch videos to get a little bit ahead, that's totally fine. Most of the examples are actually done in the videos or done in the book, so you can go through and get it. But we won't really be covering it in class. until well, the end of today. We'll just be introducing it. Okay. There's the reading and some supplementary videos. Again, some are optional, and I've listed all the things that are optional. These are all on the Straight Line Performance YouTube account. All of these that we're covering in here. One thing that's optional that I'll point out is because the slides have a mix of Excel stats and Minitab, I've put together another video that's called Linear Regression with Excel Stats, and I've made it optional, but I would highly recommend that one. The ones on polynomial regression and transformations, since we're just going to cover a little bit of polynomial regression in the class and a little bit on transformations, I want you to make sure that you watch those and cover it. And then there's one on process mapping, and I'd like to have a discussion on that one, so I'd also like you to watch that one. Process mapping, I don't want to short shrift it as a tool. It's a fantastic tool, but it's probably also a tool that you're fairly familiar with. So I'd rather use the time that we have in the lectures and the sessions together on things that are pretty foreign. Now, if I'm making a bad assumption there, please let me know. But I'd like to have at least a decent discussion about it. So I think it's like a half-hour video. So that's probably that's something I'll ask you to watch. And then in week 6, there's really only 2 videos I'd like you to watch. And we may cover all of Schuhart control charts. So you may actually find that's not absolutely necessary. Again, there's many embedded files in here. We'll use Excel stats, and you can just do the regressions and use the cut and paste, or better yet, use the record button in Excel stats to paste in these when you're done. And you'll notice there's a lot of optional ones in here as well. And then finally, the ones on DOE, and then there's a few on what are called Schuhart control charts. I think that the ones on Schuhart control charts you won't find that difficult. The ones on DOE, I hope you'll find them a bit challenging. And I've made this note here. There's a Excel stats does not do DOE, so I wrote a piece of code called and a tool called DOE Helper, which is free. Or if you want to use Minitab, you can use Minitab, but may as well use DOE Helper if you don't have Minitab. And I'll show you a little bit how to do that. We should get to that at the end of today, so you should be all set with that. And again, that's in your this is in your tools directory, and this will be helpful for all the DOE. Again, you'll notice that there's some optional ones that are in here. And that's it. There's a few more sections in your Bringing Out the Best in People book. And then finally at the end, there's the discussion. Again, remember to talk with somebody who you didn't talk to yet. So, that gets more difficult as you go on in the class. Okay, so I'll be sending that out to you at the end of the day today. So what questions do you have on this particular assignment? None yet. I'm sure you'll have plenty. And I'll just point this out. Don't be shy to call for the DOE or the regression problems, because, yeah, I know that it sort of stretches the skills in Excel stats, okay? So, and there's some conceptual things in DOE. All right. So I am going to move on if you don't have any questions. So that's that. And let's move into, I guess next on our agenda was to talk about, there we go, was to talk about linear regression. So let's get into that right away. Okay, so last time in the linear regression section, just to be quick about it, we were talking about we were talking about a situation where we had a y and an x. Okay. And does anybody remember, oh yes, and we were also in the, when we were looking at the DMAIC, we were in the A phase primarily, right? Although we said this is sort of general knowledge that you can apply in lots of different places in the business. And the key thing is, well, we'll ask in just a second. So does anybody remember the setting for this? We've got our process, we've got our x and our y. Does anybody remember what the setting is for these variables?
When you have two nums?
You got it. So I have a num as my output and a num as my input. All right? So again, even though we did this before, I'd like you to spend just 30 seconds and pick a process. Why don't you pick your process for your project, right? Your project process. And I'd like you to find a numerical output, whatever that y is, and I'd like you to think of at least one numerical input. And Gene, I'll promise not to pick on you this time. You came up with a great example last time.
Okay, thank you.
John, you did too. Okay, hopefully you've got an example and that'll work. I'll give you my example first. I'm looking at a sales process. I like using sales process, and I'm looking at maybe dollars per week is maybe a key output of mine. Notice how I always talk about the output first and then I talk about the inputs. I know the tendency is to talk about the inputs first and then the outputs. I like to talk about the outputs first and then what's driving them. All right, anyway, just pointing that out. Number of dollars per week is my key output. And I might be looking at maybe a driver of dollars, instead of dollars per week, maybe a driver of dollars per week is the number of phone calls I make, or the number of sales calls I make. Maybe that's driving the number of dollars I get. Okay. Now let's take one or two of your examples. Let's see. So let's try Steve.
I have for my process for the output is throughput.
Okay, throughput.
And then on the input side, number of operators.
Number of operators. Okay. Okay, excellent. Great example. Both numbers, no question about it. All right, Tammy, what was your example?
Mine for the output is the amount of commission dollars generated.
Dollars, okay. Commission. I'm running out of space here, so I'll just, there we go.
And then for the input was the number of brokers appointed.
Okay, so number of brokers. Hey, that's almost the same thing, isn't it? The output, whatever, in this case it's dollars instead of units, is based on the capacity that I put into it, the labor capacity. Okay, interesting. Okay, Michael, how about you? Or Mike?
Yeah, output is cycle time.
Okay, cycle time.
And years of experience.
Years experience. Okay. And all right, excellent. So one thing to point out, so this would be for like a loan processor, is that it?
Yep.
Okay, got it. And one thing that you might find, just to point this out, let's suppose like, well, I guess I'll ask you, Mike, do you for the loan processors, what kind of range of experience in terms of years do they have?
I mean, we definitely have new ones that are grow our own, so they're starting fresh in the industry, and then we probably have some with upwards of 10 years.
10 years? Okay. Yeah, so what you'll sometimes find, like in in call centers is you might have like 0 to 3, you know, or something like that. A really experienced call center person is 3 years. And in this case, you might be better off using a different, maybe a shorter time span. Like instead of years, you might do months, just to give you a little more, you know, spread on the various things. So it's just something to think about. All great examples. Great. And so what we really want to do, if you recall, is use these models. So we can make a scatter plot, and then we can use these models to find the best fit line. And that's what we've covered right now. We've covered lines, right? Even with multiple regression, we're fitting lines. And that's okay. You know, lines are very often good models, at least in certain areas, which is great. In fact, you know, not that I don't want to bring calculus into this, but you know, Newton was able to make all of his equations at the bottom of at the base level of the assumptions of all calculus is that if we make x if we choose small enough segments, we can always fit a line, and it's a good fit, and we can do all sorts of things with that. So anyway, all right, that was probably 30 seconds that you can want back of your life. I'll try not to do that too much. All right, so we'll fit that best line, and we'll get an equation, and that's going to be a y is equal to b0 plus b1x, right? And then we can use it to predict. So if we then get another point, let's say another point like right here, you know, another point on x that we care about, we can go up to here and come across and say, aha, this is the y that we get for, let's say this is my xp, my x predicted. This would be my y predicted by plugging into this equation, by putting xp in there and just getting those numbers. Remember, in practice, b0 and b1 are just numbers. Okay, so that's what we did with simple linear regression. And so, we did that. I'm going to use a different, no, I'm not going to use a different one. We did this, let's do the example that we did last time, or part of the example that we did last one, service and capacity. Excuse me, I've got a bit of a cold. All right, and in this one, our output was service level, and our input was people hours. So if we did that, and yes, I know there's a third column there. So if we did that, in Excel statistics, that would be 2 num. We're only interested in 2 of them right now. And remember, you've got to get the right output there, and there's my people hours. And I can look at all different things here, like here's my correlation, or my R squared, not all that great. If I look at my scatter plot, I might see maybe this is an outlier, maybe a couple of these are up, maybe this is an outlier right there. But it just doesn't look like a real strong thing. And we said that to do this, we went through the process of first looking at the scatter plot, then looking at the fits, which were given by these, right? Which says that the slope and the intercept are significant, so it's better than a nothing model. So the line is better than using nothing, is really what this is saying. How much better? Not much better. This is not a very strong R squared. Does anybody remember the sort of figure of the R squared that we're kind of looking for?
That was 80%?
Yeah, 80% would be that would be a pretty good one. 89, above 90 is really good. You start to be able to use models effectively probably, for most cases, around 65, 70%. But yeah, 80% is a great, that's a good goal to put in your head. So we're way away from that 80%, right? So in terms of using this model, probably would be a little bit leery of just plugging in, and we wouldn't be all that confident that we would get that. All right. So enter in multiple regression, and what multiple regression allowed us to do is it said, well, this gives me the y equals b0 plus b1x, but what if I have 2 x's, and here my thing is service level, and I had people hours. Well, what if I also took into account experience, right? Then I would, and I called this, instead of pH, I called it X1, and I called this X2. Then I would have a model that would be B1X1 plus B2X2. And maybe that would be a better prediction model, and that could help me better predict. So let's take a look at doing that. And the only bad thing about that in Excel stats is we just use 2num. We can't add another one. So we're going to have to use a different function. And it's a little bit more complicated. So let's start out by doing this. It's in the n variables. You'd think it would be in the 3 variables, but it happens to be in the n variables. And that's actually good because this handles 4, 5, 6, 7, 8, 9, 10, a million. Well, it probably doesn't handle a million. I've never plugged in a million data points. But we're going to use nnum. So n could be an integer, 1, 2, 3, 4, whatever. Okay, so we're going to choose nnum. Excuse me. And remember, it came up with this. It said number of variables to show on a data sheet. Now, I don't know why I came up with 5, but it's guessing 5. We're going to leave it okay, but here we're going to select a different dependent variable, or we could select a different dependent variable. I'm going to leave it people hours just to show you that if you do the default, all is well in the state of Denmark. Okay. Okay, so this is leaving people hours as the dependent variable. We want to change that to service level. There you go, and that's how easy it is. Okay, so we've just changed that to service level, and we can do it that way. I'm going to redo it just to show you that that's what you get when you do it with service level. Okay, so we'll choose service level, and there you go. Notice how just Excel stats put that there. Okay, so we follow the same process that we did before. We start by looking at, when we do multiple regression, we follow the same process that we did before. We look at the plots. And this time I'm going to recommend we look at the histogram, at least of the output. I'll put histograms in parentheses. And then we also want to look at scatter plots. Okay, so that's the first thing we want to do. And let's go ahead and then the next thing, well, I'll just write out the whole thing. The next thing we want to do is we want to look at the fit. And that's going to be the p-values. Remember, this is going to be a little bit more difficult, or a little bit more. And we'll also look at the r squared at the same time. And I'll show you why we're going to be looking at that at the same time. We'll be looking at both of these at the same time. And I'm just going to make one slight correction here. Instead of looking at r squared, we're going to look at r squared ADJ. That stands for adjusted. And the reason is r squared always increases as you add more variables in the model. Okay, but r squared adjusted actually sometimes decreases. And the reason we want to look at that is if you add in an irrelevant variable, your r squared gets worse, or at best it just stays the same. So we'll be looking at this, and it won't be hard. We'll just look one square over, or one cell over. So
Mark, did you say r squared
increases as you add variables?
It always increases, yes, because remember, it's the amount of variation explained in y by all the x variables. So if I add another variable, it can't decrease. It can only increase. And we can, when we do a more complex example, you'll see this. You'll see this. But it still says the same thing. How strong or how good is this regression? Finally, we'll look at the residuals, and remember the 5-second rule. All right. So let's do the first thing first. Let's look at the plots just to get a feel for, what these things look like. Okay? So let's start by looking at the histograms. So here's a histogram of service level. I'm going to put just a little bit of space on each side, to make it 60 to 90. Maybe I shouldn't have done that because now I've typed in variables. Yeah, I probably shouldn't have done that. Oh well, I did it. So how would you describe this histogram? Anybody?
It's close to a bell curve.
Looks
That
pretty.
left side starts to change it a little bit. But
Yeah, it looks pretty regular, pretty pretty much a bell curve. I'm ready to move on. I mean, I'm just taking a look at this just to get an idea. Let's take a look at people hours. Okay, so this is why I didn't want to. Oh, it made it. Yeah, that to 90. So let me go from. Let's see, what's the max? The max is 20. So let me go to 25. 0 to 25. Okay, how about let's go from 0 to 25. No, let's go from 5 to 25. How about that? There we go. How about this one?
normal.
Yeah, sounds good. And then experience level. You know what? I'm going to make this easy on myself and on you. And I'll just show you how it looks when you just let Excel stats just take it away and stop trying to muck everything up, Mark. Okay, so here we go. So here's the first one that looks reasonably normal. Second one, same thing. And experience, same thing. Okay, now the more interesting thing would be how are these related to each other? So we'll start by looking at, I'm not sure why it does that, we'll want to put on the y-axis, we'll want to put service level. Service level versus service level is not a very interesting plot, but let's take a look at, see what the R-squared is there? It's pretty good. All right, let's take a look at people hours. Well, that's what we had before. And now let's take a look at experience. So I'm going to, this time I am going to reformat this axis and make it go from 50. There we go. So let's think about this one. So this one looks a little bit stronger. I'm going to take away that regression line for just a moment. This one looks a little bit stronger than does the service level and capacity, which is right here, and people hours. And in fact, it is. There's a 70% versus a 26%. All right. So that just kind of gives me an idea of maybe what I could expect. So just a question out there. If you had to only fit one, either either people hours or experience, which one would you fit?
Experience.
Yeah, you'd fit experience because it's a much stronger fit. Now you might think that since this R-squared is about 71%, and this people hours is about 26%, boy, adding them together is going to nail it completely. And it turns out that that thinking is not quite right. And the reason is because not only are both of these variables correlated to service level, they're also correlated to each other. So it's sort of like if you wanted to predict, say, freshmen, like colleges do this, if they want to predict what freshman grade point average might be, they might look at your grade point in high school, and they might also look at your SAT scores. But both of those are pretty strong predictors, and they're both highly correlated with each other. People who tend to have good grades also tend to have good SAT scores, so they're correlated with each other. The tools on the bottom, and remember I mentioned these in passing, the tools on the bottom are meant to show you that. The first one, and I'm going to show this again just because it's in the book, but it's kind of difficult to read, is called a scatter plot matrix. To me, these plots are so small, I don't get anything out of them, so I just close them up. And I love plots, but this one just doesn't do it for me. So Minitab has a slightly better version of it, but they're both kind of crummy if you ask me. But correlation matrix actually isn't that bad. If I blow this up just a bit and move it over, we can see that, yes, if we look at things correlated with service level, the correlation of service level with itself is 1. The correlation with, let me get rid of some of these significant figures. That's pretty, there we go. It's a little easier to read. The correlation with service level in itself is 1, and with people hours is 0.5, and with experience is 0.84. That's pretty strong. But look, people hours and experience are also correlated with each other. That's given by those numbers right there. The correlation of people hours and experience. You see that? So those things are correlated with each other too. We're not going to expect a terrific multiple-regression. Well, let's go through. So we've done the plotting, and we should have at least some idea of what's going on and how comfortable we're going to be with this. So let's take a look at the next thing. Next thing is we're going to look at the fit, which is the p-values, and the r-squared adjusted at the same time. Okay, so let's go. And here it is. So we look at the p-values. One is highly significant. That's experience. That's that right there. Remember, p is very, very low, right? Much, much less than 0.05. If I make this wide enough, maybe it'll even kick into scientific notation. I don't know. I guess not. It's going to stay in scientific notation. Okay. And 1 is just borderline, right? That's just around 0.05. And I think last time I said I tend to be a little bit aggressive on this, so it's really, really close to 0.05. I'm going to keep it in. And so there it is. It gives me the r-squared overall is 75%, and r-squared adjusted is 0.73. So it looks like this is a reasonable model, and we're probably going to stop right there in terms of making it. I do want to show for just a second what's going to happen if we take out one of these. So let's take out experience level, and I want you to look at both the r-squared and the r-squared adjusted, okay? So we'll take that out. I'm going to take out experience level, and look at that. And there's our r-squared, there's our r-squared adjusted, there's our p-value. Notice that it got more significant when I removed experience. Okay, now let's look at the other one. I'm not encouraging you that you have to do this all the time. This is just for pedagogical reasons we're going through this. If I just look at experience, again, we see that very significant. We can see the r-squared is a little bit smaller than when I had both of them in the model, which was about 75%. And the adjusted r-squared is less as well. Okay, so we'll add that back in, just because both of them were significant. And now we're ready to check our residuals. Right, that's the next thing, just to make sure that everything's okay. When we had one variable, it was pretty easy. But when we have more than one variable, we have to have a little more. We have to have a little more discipline to check the residuals. Okay, here's my 5-second rule. 5, 4, 3, 2, 1. I don't see anything. Looks pretty good to me. You might have seen an outlier there and an outlier there. If you did, great, check them out. But I'm ready to move on to prediction. And so when we do that, again, let me point out right here, these blue arrows, when you press on them, you can go there. And here we are. So if we wanted to predict, for example, what would happen if I wanted to put 15 hours and I had an average experience level of 3.5, I'm sorry, 2.5 years. This would be the service level I would predict. I'd predict 78%. I hate all those decimal points. 79.7, 77.9%. Let me get rid of one more. Just makes it easier to talk about too. There we go. I'd predict a service level of 78. However, I could expect on that given day anywhere between 71 and 85. Long-term average, I'm much more confident that the long-term average is going to be somewhere between 77 and 79. Okay? All right, so that's basically it. That's soup to nuts. We just did a multiple regression. We just did 2. So before we move on to a more complicated case, what questions do you have?
If we go back to the serial correlation, the 5-second rule real quick.
Yeah. Mm-hmm.
I'm just trying to remember from, I think, a long time ago now.
Yep. Hold on a second. I'm sorry.
Okay.
I shut this down. I shouldn't have. Yes.
So maybe we see the two outliers and we want to go look at them, right?
Yeah.
If I recall, we want to look at them, see really what is it and should it be excluded. Where do we exclude them at? And is that the right course of action, I guess? Because I remember that in the older, like one there was little x, big X type stuff, but I didn't see that on this.
Yeah, so that was the control chart one. And we can't just, I mean, we can exclude it. But what I would say is, for control charts, what you're really trying to do is you're trying to find an assignable cause. And if you can, great. And if you feel that it's not really part of the normal process, then you would exclude it. In a regression, you want to be a little bit more, how can I say, more circumspect. And we might remove it if we find, oh yeah, this was just when the engineer dropped it and this is just an anomalous data point. Well, if you find something like that, okay, go ahead and remove it. Yeah, the only way you can do that in Excel stats that I know of is to literally go, this is the fourth one, for example. Just go back to the data and remove point number 4. I guess it was this one, right? Yeah. So just delete the, what? It didn't let me do it. See if I can do that. There we go. And I guess I would remove it all the way across. And I don't think that's going to screw things up. Yeah, it didn't. And now when we do the residuals, it's not going to show up there. There's a gap there. But that's the only way I know how to do it in Excel stats.
Okay. And did that probably change some of your confidence levels?
Oh, no doubt it did. No doubt it did. We probably won't see. Oh yeah, look at. I mean, the R-squared adjusted went up quite a bit, right? Because you're removing one of those outliers.
Right.
So the fit's looking a lot better. So yeah. Mm-hmm.
Okay. Thank you.
You bet. Actually, when we get to indicator variables, if I don't say it, Mike, remind me that I was going to make a comment about that. We're not quite ready to talk about this, but that's actually a nice opportunity to maybe add an indicator variable in when we come to some of those outliers. So we'll do that very soon. Okay, great question. What other questions do you have? Okay, so now let's do the full-blown one, and I'd like to do the one that is on, what slide is it on? It's on, I think it's on number 87 in your book. And then just keep in mind, in Minitab, in number 87, it's, I'm sorry, in your book it's doing it in Minitab. So it's probably best to do it in here. So what we've got here is I've got, and this, by the way, is old data. I've got an updated one, but it doesn't have all these variables. Bummer. But what we've got here is Consumer Reports data on cars. I think it's like 1992 or something like that. In any event, let's suppose that you wanted to predict highway miles per gallon, and you had a lot of other things in here. And let's say that we wanted to use all of these things in yellow right here. Okay? So, and you can imagine, I think like I said last time, like, I think I said something like Netflix uses to predict their inventory or what's going to be, they use their inventory control system. They have a predictive model that's got something like 150 variables. Or, I don't know, what some of these dating places, I don't know how successful they are, but they claim they use hundreds of variables, which just goes to show you sometimes less is more. You got to find the right variables. Any event, what we've got here is we've got highway miles per gallon, and we're trying to predict it by all of these variables that are in yellow. And I'm just going to mark them as x1, x2, x3, x4, and so forth, and build a model. Now, what we're going to try and do is we're going to try, so this is our y. We're going to try and come up with a y equals b0 plus b1 x1 plus b2 x2 plus b3 x3 plus ... plus bn xn, right, for as many variables as we had. So the problem is, if we, or the trick is, boy, this is going to be a pain in the butt if we have to keep track of all of these things. Wouldn't it be nice if I found that x2 was not significant, just to remove that from my model, so it simplifies it a lot? Or let's suppose x3 was also insignificant. I could remove that from my model. So let's take a look at that. In the last example, it wasn't a problem because we really only had 2 variables, right? So we could check them all out. We could check out one each, and then we could check out both of them together. But what happens when we have many? So I want to give you a little bit of a guideline on how to do that. Okay, so let's just go through the motions here. So I'm just going to put all of these kind of contiguously next to each other by cut and paste. Oh, it's not letting me. Insert. I'll cut and insert. Now, you don't have to do this. I'm just doing this for to make it easy on myself. Okay. So that when I don't have to, redo all this stuff in Excel stats. But you could very easily just do that. Okay. So here I go. I've got all my variables next to each other. So I'm trying to regress highway miles per gallon on 1, 2, 3, 4, 5, 6, 7 variables. So let's let it rip. And num. It says 10. Well, may not need 10, but let's just go with it. Does anybody remember what this first one was? It just says a 1. What the heck is that? All right, that one allows me to come on. That one allows me to estimate my B0. So if I look at my y equals B0 plus B1 x1 plus B2 x2 plus ... This is for my B0, and this is going to be the engine size, and this is going to be horsepower, okay, and etc. All right. And the convention is we leave this in, and I'll show you why, and I'll show you why when we finish it. Actually, I'll show you why right away. So let's, I'll show you why right now, just so that we don't have to go back. So here it is with everything in, and I just want you to take a quick look at the R squared, 72%, okay? Now let's take a look at what happens when I take this, when I take that out. Let's take a look at the R squared. Oops, I can't get it anymore. That's one of the reasons why we leave it in. Just mathematically, it turns out that you can't look at your R squared values if you don't leave the constant in. And also, you'll see that there's no B0 term anymore here. When I put it in, there's my B0, it's 23.138, whatever. Okay. All right, back to the regularly scheduled program. So we've got all these. Let's take a quick look at some of these histograms and so forth. So it looks like I've got a little bit of a skew here. How about engine size? Yeah, maybe the same thing. Horsepower? Not so much. Fuel capacity, length, those look pretty normal. Width, rear seat room, weight. Weight's kind of interesting. Not too many super light cars, but pretty heavy ones. I wonder what that would look like today. I bet you get a bigger spread because you got a Humvee at the very end, and you've got the smart cars on the left-hand side. All right. Anyway, so there's a little bit of skewness. We might want to think about that a little bit later, but at least in this example, that's just pretty mild. So we're not gonna spend a lot of time on that. We're not going to spend a lot of time on that. All right. Let's get to the more interesting thing, the correlation. So let's put, again, highway miles per gallon. This is versus engine size. Pretty interesting. Now, I don't know about you guys, but I kind of see a little bit of a curve here. And by the way, yes, that's kind of related to this whole this whole lack of skewness. And we'll talk about how we can take care of that. And the problem is it's technically not super easy, but we can do it. I want to show you how we can do it. But we're not, at least for this example, we're going to ignore that, and we're going to say, you know what, this is not too bad to fit a line. It's not too terrible. That line's not going to be too terrible. It's not going to lead me too far astray. And in fact, when we have a number of different variables, they kind of wash each other out too. This horsepower looks kind of similar, doesn't it? Fuel capacity, looks pretty strong. Look at that R squared. Length, not so strong. Width, not so strong. Rear seat room, interesting. A couple of outliers there. Might want to check those out. And weight. Well, anyway, let's just go through, and that looks pretty strong too. So let's just go through, even though, by the way, I prefer to build my models upward instead of downward. We're going to build it downward because I'm going to show you a simple technique how to do that, and it's okay. But I'll let you know, I actually prefer looking at all the plots, just having a discussion with engineers or whoever, right, or the people who are the SMEs, and then putting in the things into the model which make the most sense to everybody, and also based on the data. So, for example, I might start out with weight because that was pretty strong, and then I might add engine size looked less strong to me, but fuel capacity looked pretty strong. So I might add that in, and I might start that way. We're going to show you the opposite, which is going from the top down. All right. So here we go. Let's go on the this is the technique I want you to see. So let's start from the, I just gave myself a little more room so we can read everything there. And there's our p-values. And again, I'm going to make those smaller so we can read them a little bit more easily. There we go. Okay. So remember, in this case, when we're trying to build our model, are we interested in, are big p-values an indicator that we should keep or get rid of a certain term? Like,
If they're larger, we want to keep them.
okay, one more guess.
Oh,
If they're large, if p is low, the null must go. The null.
that's right.
Right. So if it's small, that means that there really is a significant effect with this particular variable. So here's the technique. Basically, it's pretty straightforward. We look at the p-values, and we look at for the ones that are large, and we remove those first. So the first one I'm going to get rid of is the engine size. Now, before I do that, I'm going to look at my adjusted R squared, which is 69%. And when I remove this, I'm going to see how much it changes when I remove it. If it changes a lot, I'm going to then leave it back. I'm going to put it back in the model, and I'm going to remove something else. And I'll keep doing that, okay? But generally speaking, the large ones, they're not going to change the R squared, the adjusted R squared very much. Okay? So let's go. Let's remove engine size first. Just so happened to be the very first one. That was not by plan. Okay, and in fact, the adjusted R squared went up. See, I told you it could do that. Now, here's an interesting thing. Let's look at the R squared, and I just want to make sure, because Gina's going to keep me honest on this one. I just want to make sure that when I add it back in, it's going to go up, even if the adjusted R squared goes down. Oh, boy, it's so close, I couldn't really tell. 721035. When I remove it, it should go down a little bit. Oh, look at that, 721034. So it did go down, but almost by nothing. So we removed engine size, which is very interesting. It turns out that it's not significant. Now, it could be because there's other things in the model that that essentially are correlated with engine size and take into account that, or it could be just not all that relevant in and of itself. Okay, let's keep going. What would be the next one that we might want to look at taking out?
Horsepower.
Yeah, horsepower, because it's the next largest p-value. So let's take that one out. Again, our r squared adjusted was 7.701. Okay, and boy, it just didn't change that much. 0.701 and 0.700, pretty darn close. So notice we're simplifying our model quite a bit. Now we only have 5 variables that we have to worry about, and our predictive power is about the same. Looks like we can do a little more removing. What do you want to remove next, John?
How about your seat room?
Sounds good. Sounds good. So let's remove that one. Go back here. And boy, our model's looking pretty good. You can actually stop here, but what do you say we also remove width? I don't even know what that is. Rear seat width or something. I don't know. Width, oh, maybe width of the car. And there we go. Looks like all the rest are significant. And look at that. Our r squared adjusted, still very strong. Our r squared still pretty strong. So we didn't really change all that much by removing all those variables. Lot simpler model. A lot simpler. All right, so now that we're ready to do this, and here's our model. Highway miles per gallon is equal to 39.12 minus 0.524 times fuel capacity plus 0.107 times length minus 0.007 times weight. That's pretty interesting. Weight is a small factor because the number of weight is probably very big compared to some of these others. Okay. So let's take a look at this, and let's take a look at the residuals. Yeah, and we are seeing a few of these. You probably would want to check those out, what those are. It looks like they're right around 38, 40, something like that. And this one looks like it's right around 60. Let's take a look at that and see in our original data if we could see what that is. So there's manufacturer. So we've got like 38, 39. Crown Victoria, maybe. Yeah. Maybe the Crown Victoria, and there's well, look at that, there's a Geo Metro. So maybe the Geo Metro is a bit of an outlier. And then there was one around 60 too. I wonder what that was. Mercedes-Benz midsize or something like that. Interesting. But in any case, there's a couple that are bucking the trend, and we'll need to think about those. Sometimes what you can do is you could find a pattern among these various things, and some other programs actually have some nice tools to be able to help you identify those. In any event, the residuals don't look too bad, so I would say this certainly passes my 5-second rule. Maybe I'd check out those two. And so now we could use it to predict. So if we wanted to type in any predictions for any fuel capacity or length or weight, what would happen? What would happen, for example, if we keep the fuel capacity the same and increase the weight? Hopefully we'll see the value of the highway miles per gallon go down. Let's make it quite a bit bigger. Let's make it 2 tons. And yeah, look at that. The highway miles per gallon went down quite a bit. So it's doing kind of what we think it should do, which is good. All right, so I'm going to stop here and ask, what questions do you have?
So you mentioned a program, other types of programs. Where do we find those types of things typically?
Minitab is one of those,
Okay.
one of those programs. But you can do, yeah, there's two that I like a lot. One is Minitab. And one is Data Desk, which I'm going to actually show you in just a second. But when we do transformations, but yeah, Minitab and Data Desk are two programs that are really good at helping you identify which point is which.
Thank you.
You bet. Okay.
Mark.
Yeah.
Going back, You said if the p-value is big, then we would reject H0.
Yeah, so if you remember, and it doesn't give it in here because it just gives the table, but when we did 2num, there were two hypothesis tests. The first one, and they were both of a not all that interesting sort. The first was we had this, y equals b0 plus b1x, and let's just do the one on the slope.
Mm-hmm.
Okay, our hypothesis test was h0, the b1 is equal to 0, versus ha, b1 is not equal to 0. Oh, not equal to 0.
Okay.
So that's our hypothesis test. So if p is low, the null must go, and we say that it's not equal to 0. Well, what is it? Oh, it's this. So that's really the shorthand that we're doing. We're trying to see if this is significant, if it's a significant term.
Okay.
Okay. And if you're having trouble remembering that, you can simply go back to. Unfortunately, you can't do all of them, but you can go back to the 2num. And when we go to our correlation and linear regression, here's our hypothesis test. There it is. The slope is equal to 0 versus it's not equal to 0. So that's what we're looking at.
Mm-hmm.
Mark, can I ask
Okay.
a question?
You bet.
Back on the original, when you first ran all of the lines and got all of the p-values before you eliminated any,
Yes. I'll just go ahead and do
maybe
that.
I missed it, or maybe I'm not understanding, but how come, I think it was weight that had a p-value of 0?
Let's see. Let us see. Yeah, so it has a p-value of darn near 0. It's very small, right? It only had 0 because I removed a bunch of significant figures to make it easier to read.
Oh, okay.
So weight is highly, highly significant. Therefore, the probability that we should remove weight from the model is 0.
0, right. Okay.
Yeah. Okay?
Thank you.
You bet. Okay, practice makes perfect with this stuff. The more that you do it, the better that you get at it. So we'll come back and do one more for today. But I think unless you have any other questions, and by the way, there's a couple more that are on the homework. So you'll have time to chance to practice this sort of thing. Maybe we can do one more if we have a little time at the end. I can see I'm not going to get very far in design of experiments, which is fine. We'll just do it next time. But this is one of the two big daddies of this, and everybody talks about predictive models these days. So you can see there's a lot of power in building these. So I think it's worth spending a little bit of time. Okay, before I move on, any other questions? All great questions. Okay, so what I want to do now is we'll come back to multiple regression, but I want to take a somewhat of a side trip and remind you of this one that we did before. And this was an example. We did this last time, but we had attendance is our output. Let's say you work for, I don't know, the Durham Bulls, minor league baseball team, okay? And you wanted to look and see and these are both nums, right? You wanted to look and see, this is our y, this is our x. You wanted to look and see whether attendance was driven by the advertising spend. And totally logical, and to see if we could build a predictive model for one versus the other. Now, when we looked at this before, we found, using 2num, that we want attendance as our y, advertising as our x. Remember this scatter plot? Hopefully you do. This one where it looked like, I think it was either Tammy or Gina who described exactly what was going on, and I think all of you saw it too. Steve gave the recommendation, we shouldn't spend any more than 30 because it may even be counterproductive to attendance. Now, this does have a relationship, but the problem is when I fit a line, I'm making all sorts of wrong conclusions, especially right here, right? And worse yet, over here. So, this would be a bad model to hand to somebody and say, well, just use this equation right here to show what attendance you would get. Just plug in and you'll get this line. It'd be better to fit a curve, right? So here's how we're going to fit a curve. So I'm going to show you sort of a general engineering way to fit a curve. There's lots and lots and lots of ways to fit a curve. But one way is the following. Instead of fitting y equals b0 plus b1x, we're going to add other terms based on the same x. Okay? Now notice this is not adding another variable. It's adding another term based on the same variable. We're going to add a curvature term. So the second one might be plus b2 x squared. Okay, and the third one might be plus b, and I'm going on this line because I'm running into some space problems, plus b3 x cubed plus dot, 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 and so on. Now, in practice, in engineering practice, we almost never go beyond x cubed. There's a couple of different reasons for that, but one happens to be robustness. The robustness of the model, it's almost like everything is on a knife edge when you put a ton of different terms. So I would recommend don't go behind. This is called quadratic, the second term, and it's called cubic, the third term. It's called quadratic because you get a quadrilateral, and it's called cubic because you get a cube when you use 3, right? X squared. Or, I'm sorry, x cubed. So that's why it's called a cube. All right, anyway, who cares about that stuff? Let's just see how we do it. So in Excel stats, it's actually really easy, which is great. But it's hard. The hardest part about it is where to find it. So if you want to fit a polynomial, you have to go to Extra Tools. And then you have to look very, very carefully, and you see this thing that says Polynomials. So we'll click on this button right here. Excel stats has so many things, it's confusing. And it gives a bunch of different models. Oh, but this at the bottom says linearizable. Those are just all sorts of different ways of fitting the data. You can see this fit is horrible. I'll choose one more. This one's pretty bad too. I guess I'll choose a couple. This one's pretty bad too. We don't want that. We want a polynomial. So that's given on this tab at the bottom. You see where this tab is. And we go over to that. And it's actually pretty straightforward. You see right here on the top, whoops, I'll see if I can blow this up just a little bit more and zoom in. There we go. Okay. So we can start out with degree 1. And as we add, and I'm going to make the decimal places 1, you can see that this is just our b0 plus b1x, right? Okay. So what happens if I add, I'll add 2 decimal places. What happens if I add degree 2? Let's look at the plot. Let's look at the r squared. And let's stop at a reasonable place. Wow. Well, that certainly fits it a heck of a lot better, doesn't it? I think you would agree. It went from like 26% to 87%. And but now look at the equation. It did make it more complicated, right? There's there's my B0, there's my B1, there's my B2 is right there, 0.11 minus 0.11, and here's my advertising spend squared. So you see what's going on there? Hopefully you see that. Okay, and I'm going to open this up so we can see. It gives me what the estimate is. It doesn't give me p-values on this, so I just have to use my eyeball and get the best prediction I can and look at my r squared values. Let's do one more. Let's look at degree 3. Yeah, that one didn't do too much for me, did it? It went from 86.7 r squared, 0.869 to 0.870. So using the Occam's razor that we talked about last time, These two models are about equivalent, so it's much better, I think, to use the R squared, the quadratic model instead of the three-dimensional model. And by the way, if you're having trouble reading this, it's also given down here. So our model that we would use for this one is simply, let me go to black again, y is equal to 0.724, that's this right there, plus 6.7 times x minus 0.1116 times x squared, where x is equal to advertising dollars. Okay? So that's how it would work. Make sense to everybody? Okay, I'm going to stop here for just a second for questions.
So the exercise made sense. I'm just trying to look at it and translate it back to layman's terms. As far as what would I tell my sponsor?
Right. Yeah, so it's essentially, what I would say is, make the scatter plot, okay? And to say what we're trying to do is fit an equation that best fits this. And instead of fitting a line, which would be this, we're fitting a curve, and that curve is represented by this equation. So I think the plot says a lot, but once you get into what the equation actually is, now it's just a question of, that could be embedded into an IT program or an Excel spreadsheet relatively easily. So
mainly this exercise helped find the most appropriate formula or equation for them to use.
That's right. So this is a much better predictor of where you're going to be than is this. It just is a much better predictor. This is just not a very good predictor. So fitting a different equation on a polynomial is probably the easiest way to approach it, rather than some of these other ones, linearizable ones, which are really kind of strange to most folks. Okay, so let's try one more, and see if we can do this. Okay. So again, remember, it's all about finding an equation. In the end, that equation can be used to predict, to make forecasts on, or what have you. In this case, predicting attendance based on just the advertising spend was not good, but predicting on the versus the advertising spend plus the advertising spend squared, much better prediction. Okay. All righty. Now let's see. All right. Let's do. Tell you what. Yeah, let's do. I'm going to leave this one open, but we'll come back to it before we leave. So let's do the one that's on. I don't know what slide it's on, but it is in the section on transformations, which is it's around 103, 104. It's on alligators. So in this one, we're going to pretend that we're park rangers or something like that. Maybe you folks in Florida can deal with this one if you ever move to the Everglades. Maybe it would be, or if you ever work at a golf course or something like that. Maybe this one would work for you. Okay, so in this one, essentially, what we're trying to do is we're trying to say, suppose we have some alligators, right? And we want to predict the weight of these alligators, right? Because that might help me understand the age of them or whether it's a problem. But obviously, measuring weights of alligators is going to be, or maybe we care about the health of the alligators. I don't know. But in any event, measuring the weight of the alligators is a problem, right? You need to bring out something that's a scale. It'd be tough to measure that. I wouldn't want to do it. So it's much easier to measure the length. Could we use the length to help predict the weight of the alligator? All right, now I know this is kind of a non-business example, but hopefully it'll stick in your brain enough so where you'll say, okay, yeah, I remember the curves. Yeah, that's that alligator problem. Or maybe it's the baseball attendance problem. So let's take a look at that and see if it'll work. Okay, so let's start out with 2 num. This is 2 num. And first of all, the scatter plot. So let's see. So I'm going to just change the scale here. Let's go from 45. There we go. Okay. So how would you describe this scatter plot? Let's see, Tammy, how would you describe this scatter plot?
The shape is going in a positive direction.
Shape is going positive. Good. All right. Anything else?
There's a few. I don't know if you consider it an outlier. The highest one there.
Yeah.
A few outliers to the group.
Yeah. So this is a big alligator, isn't it?
Mm-hmm.
Yeah. That's something that's maybe an outlier. And in fact, I think that, and now we shouldn't be doing this yet until we fully describe it, but if we draw the line in there, that certainly is an outlier, right? No question. And maybe this one is too.
Right.
I'm going to take that line out, and I'll ask, does anybody else see anything else? You know, maybe a curve or something like that? Yeah.
The curve is fairly flat at the beginning, then it just explodes as you get to a certain length.
Exactly. So, you know, you wouldn't necessarily do horribly if you just fit a line, but the problem is, for many of these alligators, like right here, you're going to predict that they weigh less than 0, not a very useful model, and for this, you're going to underpredict how heavy they are. So we have to somehow take into account maybe there's some curvature or something like that. So, so one thing that we could do is we could do a polynomial regression on this one, right? So we could try and fit that curve. So let's see if we can. And I wish it wouldn't start out in 2. I wish it started out as 1. So I'm going to start it out as 1. Here's my line, and certainly some problems fitting that. Let's take a look at making that degree 2. Wow, much, much better. Look at that, 98% r squared, from 86 to 98% r squared. However, still, we might have some additional curvature that we're missing. Let's just try, just for S and G's, let's try that. And that actually does maybe a little bit better. It fits that even better. Let's see if we can really kind of zoom in on that to make sure that we get it. 45, and what's the highest? It looks like it's about 150. Yeah, 150. Okay. Yeah, there we go. And that's kind of the difference between second degree polynomial and third. There's not a heck of a lot of difference, but it does look like it fits the tail ends a little bit better. So we might want to stop with that and use a third degree polynomial to do this. So think about this. You know, would you rather weigh the alligator, you know, bring out your scales, drug it, or would you rather just, you know, estimate that length and then plug into an equation? I know what I would rather do on this one. So you can see that you can fit that curve really well. Polynomial regression is a very strong predictor, or a strong technique. Now, I wanted to show you how, before we go on, how would you actually do this in Excel stats if you wanted to do prediction? Because, oh, did I close? I hope I didn't close it down. Because I don't see anything that's predictive here, right? So how would I get the prediction thingy to work? Well, here's where the convenience of that other stuff doesn't work out so well. So what you do is you have to actually add in the other variables. So let me call this L squared, and let me call this L cubed, right? And then so then I can make this equal to L, or equal to my length times my length. That's what a square is, right? And then this is equal to my length times my length. Oops, come on, baby. Oh, I must have hit a wrong button there. Times my length. And there's a shortcut for this, but I'm just going to do it brute force. Times my length. And put those in. And that actually then gives me, when I do my n num, and you'll see it turns out exactly the same. Really? Okay, well that didn't turn out the same. I crashed. Uh-oh. Uh-oh. That's not good. Something crashed it. Hold on just a second. I don't want to kill the meeting. This sometimes happens. I guess I didn't hit there. Let's try this. There we go. Okay. Got back. Yeah, something is bizarro by Ferraro there. I'm not going to save that. All right, there we go. And when we go to multiple linear regression, there it is. There's our R squared. And there's our length cubed and all that. And you can do all the prediction you want on this. Okay? Likewise, if we go back to the data, you'll probably recognize this number then too, R squared. So it's kind of a combination. The nice thing about it is, but you have your residuals and all of that stuff. Oh, I didn't show you the residuals, but check this out. I think you'll find this kind of illuminating. Let's check out what happens to the residuals when we just have the length. Remember, when we just have the length, it's going to look, there's our weight, there's our length. It's going to look weird. Well, what happens is if we look at our residuals, and we already know that it's going to look this way, but the residuals, when we look at the residuals versus fitted value, they have that curve. You see that? Now look what happens when we add in our other variables to the residuals here. I'm just going to add them both in. The residuals actually, whoops, not length squared, length cubed. The residuals actually become, much better. Don't make me a liar here. There we go. Look at that. Now we don't see that up and down pattern or that curved. And in fact, this is not that big alligator is not an outlier at all for this data, right? It's kind of normal. It's this one that's the outlier. It's this guy that doesn't quite fit the data as well as we would think. But this big guy fits pretty well. This model. This model fits that big guy pretty well. Okay. Questions on this one? I know it's a bit of a stretch. I get it. If you haven't fit equations before, this one's probably pushing you a little bit because it's saying, all right, all we're really trying to do is find an equation that fits that curve, that scatter plot better than what we've got right now. Okay? That's all we're really trying to do. Okay. What questions do you have on alligators and all that kind of stuff? Okay. Let us, like I said, the most important one is simple and multiple. Those are the two most important by far, but this can be a very powerful technique if you get it. Okay, let's do, because I'm going to shut everything down. There we go. Okay. Before we move on, let's do customer satisfaction, and I'll ask for your help on this one. So this is one of the examples that's in the book. This is one of the examples that's in the book. And for this one, we have customer sat, and is being driven by a number of different things. Okay, now we've simplified it. You can imagine like giving somebody a questionnaire of like, I don't know, typical customer satisfaction survey. They give you like 20 questions or something like that. And those 20 questions are divided into essentially 4 sections, whatever those sections are, A, B, C, and D. And the composite scores on each of those sections are what's going to be driving these scores here in A, B, C, and D. So I don't know, if this was customer satisfaction for a hotel, maybe the first 5 questions were about the room cleanliness, and the second 5 questions were about the amenities, and so forth. Okay, hopefully that setting makes sense to you. You can see right over here, these are numbers. Okay, so what we want to do is we want to build a model based on this that says, let's get an understanding of what we could do to maybe what would be the best thing to move the needle on. Should we work on the questions that are on Section A, Section B, Section C, Section D? Should we improve one of those sections or 2 of those sections? And if we did, what would we get for that? Okay? Does the setting make sense to folks?
Yep.
Okay, great. So let's go ahead, and this time I'm going to let you guys do it. So let's see. Steve, can I ask you to be our volunteer today?
Okay.
Or
So
one
we can generate. Sorry.
One
so
of
we're
our
gonna generate the plot.
one of our volunteers. Yeah. So I'm going to give you all the ability to move the mouse, but let's just start out, and I'll open up Excel stats so that we have it. And so I'd like you to go ahead and build this. Let's start out. Let's build the model, and let's start out doing what we do best. So let's get it into the right place in Excel stats. So it's up to you.
Okay. First, let me activate that.
Mm-hmm.
Okay. So we're gonna select the data.
Great.
Okay. We're gonna do num
You got it.
analysis.
Right. So our overall is customer sat. So that's good.
Yep. Yep. Just leave everything.
Okay, so it looks like we have all the data in, which is great. So let's start from the start. What do we do first?
I'm not seeing anything. Oh, there it is. It was slow refreshing on my screen.
Oh, okay. Sorry about that.
Okay. So we have all the data in.
Mm-hmm.
So we'll go to tab 1
Okay.
and look at some of the plots.
Okay, sounds good.
Look at just the shape of this plot here. Looks a little bit uniform in a way.
Yep.
Not a typical bell curve. Look at some of the other variables.
Mm-hmm.
Okay, the A kind of have a normal shape to it.
Yeah.
With some okay. B, a little bit skewed to the left,
Okay.
to the right, I mean.
Mm-hmm.
My computer is very slow for some reason.
Yes, you're doing great.
Okay, look at C again. You see, somewhat of that bell shape.
Okay.
And D.
Okay. So, nothing really popped out as like, oh my gosh, it's really super skewed or anything like that. So let's move on to the next set.
Go to tab 2 just to see what's there.
Great. Okay, so let's do me a favor and put in where it says pair by pair. On the vertical, let's put overall, because that's our overall customer satisfaction. We'll put our driver, I'm sorry, our dependent variable over there, and on our horizontal, let's put, we can start out by putting A.
A, right.
So what we're trying to look at here are, does this look like it's correlated with it?
Right. So we'd look for only outline points.
Mm-hmm.
Nothing outrageous. No, there's a few that over the top here, perhaps, but nothing significant.
Mm-hmm.
So it's not a bad fit.
Okay.
But the R2 value is very low.
Yeah. Yep. Okay.
Okay. So I'll move on to the next one.
Sounds good.
It could be, that's very well correlated, with the R2 value of 85.
Okay.
Look at C. And this one, not 54, not great, but better than A.
Mm-hmm.
But there's a few points on the outside here.
Okay.
And lastly, D. Whoa.
That looks like nothing, right?
Yeah.
That's a blob.
Wow. Okay.
Okay.
Then I guess we'll then move on to the multiple regression tab.
Okay. Let's stop just before we do this. I'm going to have you look at one more thing. And press the button that's next to correlation matrix near the bottom.
Multi-plot?
No, correlation matrix.
No, that one. Yeah, that one. I'm sorry.
Mm-hmm. All right. And I'm just going to make this a little bit easier for us to read, okay? Take out all of those significant figures. Okay. And let's just look on the bottom half. And do you see any things that are big numbers for those correlations? Like, I don't know, anything that's around 7 or so?
Right. Well, B to C,
Yeah.
and well, just that. Yeah, B to C.
Basically just that. So this one right here, and by the way, the upper half, you see how this divides the center. This is everything correlated with itself, which is not that interesting.
Right.
But
Right.
these right here are the same. You see the top half and the bottom half are the
Just
same? Yeah.
Yep.
So the upshot of this is, I don't know if you remember in the curves, and by the way, it's a challenge to your short-term memory in multiple regression. But when we looked at the curves, we found that both B and C were highly correlated with the overall, but unfortunately for us, they're also correlated with each other. So chances are that if one of them's in the model, we might not get that much bang for the buck by adding the second one in. So it's just something to think about as we build the model. Okay? All right, great job. I'm going to ask somebody else to help me build the model now. So we've looked at these correlations, and thank you, Steve. So let's see, John, can you take it from there?
Okay. So let's see. Computer's slow as well.
Okay, just do your
Okay.
best. And actually, if you just talk me through it, why don't you just talk me through building this model, and
Okay.
I can move
Okay.
the controls.
Okay, great. Let's see. So we want to remove the highest p-values. So number 1 would be the first to go.
Okay, so what is number 1? Before we do that, what does number 1 represent? What is that?
What specifically is it?
Yeah.
Oh, I'm sorry. That is our B0.
Yeah. So I'm going to remove it, but I'm going to come back here. And remember,
Perhaps
we're going to be
so.
keeping our eyes on the R-squareds and R-squared adjusted. So when I remove it, remember what happens?
Yeah.
Probably remember now. It's like, oh, yeah, I lost my R-squared. And by convention, we just leave it in. Okay?
Right.
Okay, so I'm going to put that back in. But good on you. So, okay.
All right. How about D?
Yeah, and that should make some sense, right? Because when Steve looked at it, it had like, its scatter plot was nothing, right? So let's go ahead and remove that. So all is making some sense. Now notice when we remove that, the p-values change. Okay.
Okay. Then C.
Looks like we can remove C pretty safely. And again, I'm looking at that R squared adjusted. It hasn't been changing at all. It was 86 and it still is. And so now what do we remove?
Well, we could try, I suppose you could try the A. Well,
Yeah.
that would,
Okay, go ahead.
I was going to say that would, wouldn't that destroy the model?
Well, it makes it a pretty simple model, right? so now I would say it's up to you, because technically, that's certainly greater than 0.05, but I tend to be a little bit aggressive on my model, so I might stop here, or I could take it out. It's up to you. Either way,
We'll take it out.
Take it out. Okay. So there we go. We can take it out, and certainly everything else is significant, and we still have a pretty good R squared. And we've certainly made our model a lot easier, right?
Right.
So the other thing is that we could do is, not only use this for prediction, but not to be dumb about this, but what area now are you going to focus on for improvement?
B.
You're going to focus on B for improvement, right?
Right.
And do that. Now, we didn't notice this, and I'll just point this out. We didn't notice this, but when we... Oh, that's not good. Why did everything... Oh, I know why everything went away. It's because I'm just going to add everything back in. I hope that's why it went away. It could be wrong. There we go. Okay, so we got it back. We didn't notice this, but let me make it go... Everything goes from 0 to 100. Now, if I do that, watch what happens. Check out where B is. It's tight and it's near the center. Check out where A is. A is kind of all over the place, right? So certainly there's some scope for improvement on A. C is pretty high, so it makes sense. Maybe I don't even want to try and improve that all that much, because it might be hard to. And there's D. D is pretty tight. Maybe I have some room for improvement, but it turns out that it's not really related to customer satisfaction. That may be giving bad answers or whatever, but it's not really highly related to customer satisfaction. So, just by looking at these plots, we could also start to say, yeah, maybe it makes sense that we can move the needle on this one. And it's kind of a happy coincidence, because moving this up versus this one, we've got to both tighten and move up. That's often a difficult challenge. Now, I know it's kind of hard to do in the abstract, but if you can imagine, a battery of questions that's aimed at, the cleanliness of the room versus the amenities or something like that, helping us focus on, okay, for this hotel, let's focus on just making sure the rooms are clean, and we're going to get the most bang for the buck. Maybe that's a good way of articulating it, and we've got a nice model that we can then also use for prediction. Now I'm going to remove these again, and we can come to here and use this for prediction, and etc. What happens if we can just move that up to, on average, 70? Well, our satisfaction is going to go way up. We would predict it's going to go way up. So that lends a lot of credence to that sort of thing as well. Okay, nice job, guys. All right. So let's try one more, because I think we're going to pretty much do just a couple more things here. I'm going to cover dummy variables now, or indicator variables, and I think we'll call it a day. But to do that, I want to segue into it. So I'm going to open up this temperature data again, and hopefully this is going to be irrelevant to us in the next couple months, because this is January temperatures. And I don't know, it feels like it's a little bit better today. I hope it's changing finally. All right, so if you recall, we had a bunch of cities, and we had the latitude and longitude, and we had the January temperatures. So this is what we care about, the January temperatures. And we wanted to see, when we did multiple regression, and I'm going to select all of these. I'm just going to select these two. No, I'm not going to do that either. What we wanted to do was see if we could build a model that can help predict January temperature. This is supposed to be, I think, average minimum temperature, or it's the average temperature for this particular latitude and longitude. So Tammy, I'm going to ask you to go ahead and build that, see if we can build that model, okay? So just January temperature versus lat and long.
Okay.
Oh, what the heck? Why not select that west coast also, and we'll come back to it, but we'll just build it for lat and long.
Okay. You give me control here. Oh, there it is. Okay.
You got it. Love it. Looks pretty good.
Sorry, it's taking forever. Can you see it? Because it froze up on mine.
Oh, I can.
It just looks like it's clocking, like we can't see it moving.
Oh.
It
Okay.
should take, oh, there it goes. It's taking a while.
Okay, did
I
it go?
still can't. Let's see.
Okay. Yeah, maybe you've got a slow connection. All right, well, maybe you can just walk me through it, if that works.
Okay, but I can't see it. Mine is still a blank screen.
Oh, okay.
So-
How about now?
No.
No? Okay, shoot.
Oh, there it is. Never mind. There it is.
Okay.
Came up.
All right, so what do we want to do first?
Go to the tab 1.
Awesome. Okay. So we'll look at the histograms.
Yep, that looks pretty basic. That's basically like a bell curve.
Looks pretty good.
Yep.
Same. Now that one's kind of interesting.
Uh-huh.
There's nothing that's really concerning. I don't see anything that's like super skewed. Like if we took a look at that alligator one and we put it in here, we would have seen something that was super skewed. But here we're not. Okay. So the good news is we probably won't have to worry about adding polynomial stuff into here. We don't need to worry about it at all. Okay. If we see the really super skewed stuff, it might mean, oh, maybe one of them's curved or something like that. So I need to check that a little bit more carefully, and maybe I'll need to add a polynomial term. Okay. Next stop on the train will be the scatter plots. So let's take a look at that. I'm going to put January temperature back up. And you know what? I'm going to remove that line. And then let's just take a look at it. Here's January temperature versus latitude. What do you think?
Mine's still back on the histogram.
Oh, my
I
goodness.
can't see it either.
Really?
Starting to move now.
It's coming.
Yeah, it's just running like a few seconds behind all day.
Oh, that stinks.
I still don't have it.
Okay. How about now?
No.
I can see it.
It's on.
Oh, there it is.
Okay.
The R
Okay.
squared is pretty good, a little over 70%.
Yeah, and it certainly looks like a line there. You see anything else there? Just I'm mentioning this in passage. Remember, when we read those scatter plots, we look at, yes, we look at lines, and that looks like a pretty good line, but we also look for other things.
Outliers?
Yeah. So do you see any outliers there?
Yeah, if you're going from to the right side, the 2 there.
Yeah, maybe these two right there.
Mine's froze again. I can't see. I
Ugh.
apologize.
Why is this so bad right now?
There, now I can see.
Okay. Those two that are out there?
Mm-hmm.
Yeah. Okay. I'm going to go ahead and erase that. And I'm sure glad I'm asking you to do this, because otherwise I wouldn't know how slow everything was going. Okay. All right, so let's take a look at the latitude-longitude one. And how about this one?
Very low R squared.
Yeah. Does not look like there's much of a correlation at all.
No.
All right, so probably want to, when we look at this model, we probably want to take the latitude with, that's probably going to be our most important one, and our longitude might not be all that important. But let's take a look at it. We'll keep an open mind. All right, so when we look at this, let's take a look at the p-value. Can you all see this one?
Yep, I can.
Okay. So the interesting thing is if we look at these p-values, ooh, I want to get rid of West Coast. If we look at these p-values, they're both significant, right?
Right.
So this would mean essentially keep these in the model. Keep both latitude and longitude in the model. Now, what the heck is going on? How could longitude be significant? How can that be? Because when we looked at the relationship between these two, it looked like it was not significant. How could that be? Anybody remember? Okay, I think last time I described it as kind of the shoe effect. And I said, you know, let me give you a penny. And if I give you a penny and if I put that a penny into one of two shoes and hand you the shoes and I say which shoe is heavier, you probably couldn't tell the difference. But if I gave you just the pen, you know, I put a penny on your hand and one penny on one hand and nothing on the other, you probably could tell that weight of the penny. Or you can imagine maybe something a little bit bigger than a penny. So what's happening with regression is when we regress out latitude, what's left is actually longitude can explain a little bit of that. Not a lot, but it can explain a little bit, which is pretty interesting. So that's how a lot of these multiple regression things work. When I remove longitude, you can see that r squared is about 72%, 71%. I add longitude back in, and it's a little bit better. It gives me maybe 2% more, but that 2% is significant. So that's interesting. Well, I find that interesting, and I find it helpful as well. Now, before we move on, let's look at this plot again, and let me know when you can see this. Can you see the January temperature versus latitude plot?
Yeah.
You can all see that. Okay. So what I want to do is I want to explore a little bit on these outliers, okay? So if we take a look at these outliers, these are the ones that have about a temperature, January temperature of about 32 or so, and latitude of about 50. So maybe 46 to 50. So I want to find those on here, and let's see if we can just find a couple of them, and let's see what they represent. I'm going to go into the data. So if I look for a latitude of about 50, and boy, it'd be nice to have a better tool to do this. Maybe what I could do is just sort it by that. Okay, so it's a latitude of about 50 and the January temp of about 30. There it is right there. So that's interesting. That's Seattle. And if I look at the next one up, that's Portland. So those two outliers were Seattle and Portland. Is there anything that's common about Seattle and Portland?
Both right next to the ocean, same part of the country.
Yeah, so they're kind of like the same part of the country. So Mike, remember when you said the whole point about, oh yeah, maybe if I look at those residuals and I find one that's an outlier, maybe I can remove it. What I'm going to show you is there's a way that you can actually incorporate it into your regression to make that regression better. So sometimes by looking at outliers, you can find patterns to those outliers. Like for example, here's a few other ones. That one has a relatively high latitude and a pretty high January temp. That one's San Francisco. There's a pattern emerging here, right? These are all West Coast cities. Here's Los Angeles. So what if we marked all the coastal cities on the west? Maybe we could also take that into account. So that would be, I guess, Spokane, Portland, and even Spokane is not so much on the coast. That's actually past that last mountain range, but we'll call it West Coast anyway. And what if we added that in there? This is called an indicator variable. So what we're doing is we're going to add in an indicator variable that indicates whether it's West Coast or whether it's not West Coast. Okay? Does that make sense? Conceptually to everybody, does that make sense?
Yep.
So we just created that. It's like an on-off switch. It's either 1 or a 0. It's on or it's off. Okay? So let's see if we can add that in to our regression. And of course, the answer is going to be yes. And when we add that in, let's first of all look at our multiple regression. It's about 73%. And when we add that in, it can be a lot stronger. Look at that. It went from 73% to 89%. So the combination now of latitude, longitude, and whether it's a West Coast city, now I'm explaining 90%. Now I've got a darn good model. The important step in that one was realizing that we don't just have to use numeric variables. We can add in categorical variables. Okay? So that's kind of the important thing to add in there. Now I'm going to do one more example for us. And we really should do the residuals analysis too. By the way, I'm going to show this one more time. Here's the residuals analysis without that. And we should see those outliers. There they are right there. There's a couple of the outliers. And when we put in the West Coast, which I'm going to do right now, we should see those residuals go away. And they did. They went away to a large extent. Instead of being up there, they're now here. And you really can't see. You really can't see them in the fitted value plot.
The
Are you showing the screen?
Oh, we're having latency again. Oh, dang. I've got a really good internet access. I don't know what else to do. Must be problematic, though, here today. Sorry, I'm so sorry about that. Can you see it again?
Not yet.
No, not yet.
Hmm. Let me know when you can see it.
While we're waiting, when are you sending the homework out? I'm sorry.
Oh, I'm going to send it out right after the right after class. I'll send that out.
All right, we can see the multiple linear regression now.
Yeah, that's not even where it's at. So I think that what we probably want to do is I'm going to go over. So if you can flip to, I'm really sorry about this. If you can flip to the example that is in, we're talking about indicator variables, and if you flip to the example that is on slide 161, okay? I'm going to do this example, and we'll do the whole thing in Excel stats, and I'll show you basically what are some of the, it sounds really cool, and it is, that you can do these dummy variables or these indicator variables, but we're going to do the forms, I'm going to do that forms example. So in this case, we have a setting, and again, if you can just let me know when you can see my screen again, that would be very, very helpful. That'd be extremely helpful.
We can see it.
Okay, so a couple of you can see the screen.
Yeah.
Okay, so what I've got here is we've got a situation where we've got a company that looks at processing electronic forms. Remember before we looked at they were looking at the cycle time that it takes to process. So it's very similar, Mike and Gina, to your problem that you have, or your project that you're working on, and actually similar to yours as well, Tammy. They're trying to reduce that cycle time, and they thought that by looking at the number of fields that the person would have to put out, that they could help predict that. That's all well and good. But the problem is when we did that, and we looked at the n num, or I guess we only looked at 2 num, we got that the regression was just not that strong. It was like a 49% R squared, 49, actually about 50% R squared. So we'd like to improve that a little bit, and somebody came up with the idea that said, well, it's not just the number of fields. What if it's the type of form as well? So what we can do to do that is we can add that into our regression as well. So Mike and Gina and Tammy, can you see the screen?
Yeah.
We're doing okay?
Yes.
Okay, good. So realize that we can come back to this on next time when we come back, but I want to do it just for the recording's sake so we have it. And I do realize that we're at 12:52. So I'm going to move fairly quickly. I'll stay around for questions if you have them afterward. But I'm going to add form type into this. So let's see how we do that. Now, the first thing I think we ought to do is we probably ought to do a one num one cat analysis to see if form type is really driving processing time. And if it is, great. That means that maybe we can focus on this. So I'm going to first do one num one cat. And boy, it sure does look like, and I don't know if you can see the box plot right here. Can you see the box plot?
Yes.
Okay, great. If you can see the box plot, you can see that box plot's all over the place. So chances are, yes, you can, yes, this form type is going to be important. For example, E is very low and consistent. B is fairly high cycle time. So how can we add that into a model to actually make a prediction? So I just want to make sure that we all understand this. If you're just looking for ideas for making improvements, you've already found a good idea. Hey, maybe we can also take into account form type, and let's focus on improving B, and let's focus on improving D, and let's leave E alone, and we're good. Okay? Because remember, lower cycle time is good. Okay, so this is all about just building a model. So if you want to build a model, listen in. So the first thing is we noticed that there were types A, B, C, and D. And I'm just going to remind you of that by clicking on one cat. There it is, A, B, C, D. So here's what we have to do if we want to create indicator variables. Remember, they're all 1 zeros. I can't just add in A, B, C, D into the model. I have to create switches that are all 1s or all 0s. So for example, this is if this thing equals A. I'm just going to make it equal this thing right here and there. Then make a 1, otherwise it's a 0. Okay. And I'm going to take that out. There we go.
So Mark, it's running slow. So in column D you have an A, and in column E you have a B, and that's, have you typed anything else?
Yeah, so I'm typing in if-then statements. So
Okay.
basically, what I want to do is, like in column D, I'm going to make a 0, 1 variable that's 0 when it's anything but A, and it's 1 when it's A. So the first value for 47.65 would be 0. The second one for 63.13 would be 0. The third one for 58.76 would be 0. The fourth one, 34.88, would be 1 because that's form type A. Make sense? It's a switch. It's 1 when it's A, and it's 0 when it's any other form.
Okay.
Okay? I'm going to do that same thing for all of these others. And yeah, you have to somehow do this in, like in Excel. It's one if-then statement. And so here's my switch for B. It's a 1, 1, 1, 0, 0, 1. You see how it matches up with B. And then for C, it's a bunch of zeros until it hits C. And for D, it's a bunch of zeros until it hits D. And for E, it's a bunch of zeros until it hits E. Okay? So now I've created all my variables, and I'll just mark those so you can see it a little bit better. Are we still having a tremendous latency?
Yeah, we're about
Yeah.
a minute.
Yeah,
Fine.
that's cool.
What's that?
Yes.
Yeah, bad latency. All right. Well,
There it goes.
Yeah.
okay. So hopefully everybody can see this now.
Yeah.
Okay, so I've got a switch for A, I've got a switch for B, I've got a switch for C, I've got a switch for D, I've got a switch for E. Okay, so they all add up to 1. You see, so B is, on that first data point, it's a B type. So every other thing is 0 and B is 1. Second one is B, same thing. The fourth one is A, it's a 1 for A and 0s for everything else. So I don't know how else to do it in Excel. That's the shortest way that I can do it. But now we're all set, and so now we can select these and we can do our multiple regression. So I've selected all the fields, and I'm going to choose processing time as my dependent variable. And now it's a question of just keeping all the significant ones in here. Now, of course, we should go through and we should look at all the data. We should see which ones are drivers. For example, with processing time versus, I don't know, let's see, A. It looks like there's a difference, right? I see a slope on the line. When, on the other hand, when I put in C, it doesn't look like there's a difference between A and between a 0 and my 1s, when it's on and when it's off. It looks pretty flat. Okay? So it looks like there's not really an effect for C, but there is for A. All right? So I'm going to go ahead and do my multiple regression. And the first thing is I see a bunch of p-values that are 1, and so it looks bad. So for now, just realize that you just need to remove one of them, and it doesn't matter which one you pick. So we're going to go ahead and pick, I'm going to go ahead and pick E. Hopefully you can see this multiple regression table. I'm going to pick removing E, and then that'll give me a bunch of p-values. There we go. Now I got my... Hello?
We're running in batches. We're about constantly a minute behind, it seems like.
Okay. All right. Well, I'm just going to finish this up, and then, like I said, I'll stay for examples. If you go through and do this one, you'll see that when you remove a bunch of the switches, you remove the first one, and your p-values come back. And then you can go on, and you can build the model just like you would any sort of multiple regression model. You can see the model is building for A, B, C, D, and so forth. So it works exactly the same. The key is to be able to build those switches, those switch variables into that. So unfortunately, that's a real bummer that we've kind of lost this connection. I'm going to close this down and just take a moment to recap. We really talked about regression today. We talked about multiple regression, and if you take anything out of this, make sure that you take out that multiple regression. We talked about then polynomial regression, and finally we talked about indicator variables. So at this point, that's basically all of the linear regressions that we're going to cover, and it covers all of the modern techniques that you really care about. The one that we've left on the table is something called logistic regression, and if you really want to know about that one, I'm not going to spend class time to do it. There is a video on it, and you can do that. But I will send out the, so that's it. We're not going to cover any more regression, so that's the good news. I don't know. Hopefully you get a flavor for, the real creativity that's in here, and hopefully the power as well. To be able to make predictions is a very powerful thing. So building those models can be pretty powerful. All right. Okay, so I'm gonna call it a day. I will send out those assignments to you very soon, and we'll talk to you later. Okay, have a good day. I'll stay on the line if you have any questions.
Thank you.
I'll stay on the line.
Thank you, Mark.
Okay, see you.
Thank you.